let's get started. The purpose of this podcast is to look a bit more closely at these features you would have in your diploma formula booklets, dealing with equations of straight lines, slope or gradient formula. We'll take a look at some quadratic quadratic function um, issues, maybe not so much this yet, that's coming later, and solving with, of course, the quadratic formula, some call it the general formula, and a brief mention about the discriminant. So let's consider something really straightforward regarding a linear function, something as standard as given some linear function y is equal to g of x, it's passing through 2 points. Can we simply show that the line can be written as y is equal to 2x plus 1? Not a challenge, since using a y equals mx plus c approach, or maybe y equals mx plus b, depending upon your culture, first you want to focus on finding the slope or the gradient. Of course, there's a gradient formula to help you with that. Difference between the y's divided by the difference between the x's, sort of a rise over run issue. I tend to grab these positive values first, right? So 3 minus a negative 5, I find a bit more convenient. You go back and grab 1 minus negative 3, so that keeps things largely positive, and you're dealing less with negatives. So at that stage, you're pretty straightforward. You've already confirmed the 2 of the slope that you needed, because there it is right there. Plug in whatever point you so choose to satisfy the line, and of course picking the point that's positive is probably the best thing to do here. So letting x and y be the values respectively, you grab c equals to 1, and there it is. Pretty straightforward stuff, certainly prior learning relative to dp. So let's consider that y is equal to 2x plus 1. Think of it more now as a function. So here it is using a slightly different notation, kind of a mapping notation, which you could see in dp as well. And here's a quadratic function. So let's look a bit more closely at some of the issues associated with now not only linearity but also a quadratic. So let's find the zeros of this function f that's given. Let's do it first by factoring, then we'll do it on the next slide using the quadratic formula, and then we'll exploit the GDC after we nail down those two features, which are parts A and part C, more sort of paper 1 non-GDC approached. And we'll mention briefly what this discriminant might mean relative to the part that's under the square root symbol in the quadratic formula. So there it is. There's the function in question. We need the zeros, just equate it to 0. And factoring is something that we spend some time with in the program, setting up a couple of parentheses. What times what gives you the 2x squared? Well, that's sort of the first times the first element. You've got this last times last piece, which has to multiply to be the 1, and then this combination of 2x, 1x in the middle. You throw the signs in there to account for the fact that we have to have a positive here, so positive 2x minus the 1x is what accounts for that. Whether or not you're up to speed on factoring in general, that's a quick snapshot of it. You can sometimes pretty much get around that in the course just using the quadratic formula. I'll show you how we can do that. So if two factors multiply to be 0, of course, then one of those factors is 0, the other one is 0, or they're both 0, because 0 times 0 would also equal 0. So the x value that zeroes out this factor, that would of course be 1/2 when you solve that little equation. This guy's directly -1. This is not a requirement within IBDP, although designating one of the solutions or the roots or the zeros, they're all synonymous terms, with x sub 1 and x sub 2 with subscripts is a good idea by way of just organizing your work. So same problem, let's jump down to looking at finding the zeros using the quadratic formula. That, of course, is right in the formula booklet, not Facebook, by the way, but your formula booklet. So crank it out. It's just a recipe, right, where A is 2, B is 1, and C is -1. So when you crank out what you see, what's algorithmically achieved using just a recipe here, we end up getting that the x values are going to look something like -1 plus or minus 3 over 4. Some students get a little bit challenged by this sometimes, especially if this is not a perfect square here, and maybe you've got something like -1 plus or minus the root of 5 over 4. The best way to pull that apart is, of course, we need -1 plus 3 over the denominator. There it is right there. That's one of the roots. And then -1 minus 3, that's the other root that's right here. So we end up, not surprisingly, getting the same two roots. If you want to know the truth when it comes to the comment I made about factoring, if one of the roots x is a half, you could actually work backwards from that. Multiply both sides by 2, and then bring the 1 over, and you would actually have the factor. And if the other root is -1, you could bring that over and get +1. So you can work backwards from those roots and generate these two factors. So truth be told, you can backdoor your way into factoring. Have a think about that. So, a comment there about the quadratic formula and what actually controls the nature of the roots. That's coming a little bit later on a future podcast. The part that's under the square root symbol, that's what's allowing for this plus or minus value here. That's what's allowing for either two roots, or in the case where this would be 0, you would only get this value here over the 4. You wouldn't get this plus minus 3 component. So what's coming later is the role that b squared minus 4ac plays, which of course is the so-called discriminant, and that was on the first page that we saw in the formula booklet as well. So we'll come back to that later. GDC, throwing the function in question into the y equals, making sure your stat plots are turned off, because when that stat plot is on, it can sometimes create an explosion. So your graphing, I tend to go zoom 6. That takes me immediately to a standard window. When you hit zoom 6, you'll see a spread of window values there. All I did was slightly modify the window from -5 to 5 to get a slightly better picture. When it comes to actually trying to get the zeros, of course, we're talking about where this guy crosses the x-axis. That's a 0 or a root, or the x-intercept, as it turns out, and that guy right there. So we're expecting -1.5, and not surprisingly, when we go second calc to bring up, second calc is one of the most important features going through DP mathematics. Second calc gets you this field of choices here, this menu of choices. We're grabbing the second one for the zeros. Pretty classic left bound, right bound to set sort of extreme boundaries on where the GDC is going to be looking. So it says guess, you hit enter again. It's trying to look between these two left bound, right bound values, and of course it throws -1 into your lap. So not surprisingly, we were able to confirm that x equals -1 is one of the zeros, and you could actually go ahead and try to confirm that x equals a half is the other one. IB is moving more towards solving things like inequalities. So let's try to find all the x values such that this function is greater than or equal to g's inverse. Well, of course, we need g's inverse. We'll talk about both interval notation and set notation, and we're going to use a 3 significant figures standard, which is pretty much your standard unless you're asked otherwise in terms of your rounding standard through all of DP for the 2 years. So firstly, of course, we need to actually find the inverse function, because we only have g of x as a linear function, and there it is right there. So the standard method, if you will, involves inverting, right, hence inversion or inverse function, the x and y variables, then solve for y in terms of x again. So that newly created function, that'll be our inverse. So here we are with the given g of x function. So when you invert, right, simply replace y with x and x with y respectively, and then resolve for this y value, throw 1 over to the other side, divide, and what's emerging will actually be the inverse function. I purposely put down 3 different representational forms here, right? So you divide both sides by 2, and you're here, which of course, because 2 is a common denominator, you can write it like this. And dividing x by 2 is the same as multiplying x by a half. All three of these forms are equivalent. All three represent the inverse, but I'm going to grab this guy here because I'm more a fan of fractions than maybe you are. So now we want to know where the given quadratic is greater than or equal to the newly achieved inverse function. So let's exploit the GDC there. So basically the question is right here, and where y sub 1 in your GDC is f of x, and where y sub 2 is inputted as the inverse, I want to know the x values for where basically the one curve is above or equal to the other. And so where is the blue curve above or equal to the red curve? That's essentially what you're trying to do here. So here's exactly where they're equal. So it looks like from this x value to the left, that's where this blue curve is above the red curve. Here it switches in this interval in here. And then, of course, this value right here, this is once again starting from this x value to its right. That's where all of these y values are above these y values. So you're just looking for the interval of x's where that takes place. So what I did is I just used the intersect feature, right? Again, second calc to bring up the intersect feature to take a look more closely at the intersection of these two curves. That's also a sort of a left-bound, right-bound thing. You got to get to the left of the point on one of the curves, enter on it, it jumps over to the other side of it. You bring the cursor across and it finds the intersection point. So that intersection point represents the x value right there, and we need everything to the left of that you can start to see emerging here. And then if you do the same, play the same game with this guy here using the second calc intersect feature to find what ends up being 0.390, and then everything to the right. So in set notation, what we have there is that the one curve in blue, those y values, are above or equal to the red values for all the x's less than or equal to these, or all the x's greater than or equal to what you see there. So you don't need to write it down as sophisticated as this at the SL level. If you simply just say it's x is less than or equal to this guy here, or x is greater than or equal to this, you're fine. Interval notation, that's trying to say it's the union between two sets. You can see non-inclusive of negative infinity, so that's saying all the way from negative infinity, comma, up to and inclusive of this value here, the negative 0.640, and then jump over this middle place here, and then you're uniting that with being inclusive of the 0.390, because that was right here, and then everything to the right. That's interval notation. That's one way to exploit the question, or the solution, I should say, using the GDC. Another way could be to simply say, well, if we're trying to find that solution, what if we just drag that over to the other side? So that's where the difference of those two functions will be 0. This is actually my preferred approach. Then I've got that these are my y sub 2, y sub 1 values, if you will. I can actually put the cursor on the GDC and disengage each of those. So notice that they're turned off, and then I can actually go to my variables menu, that's down here, and arrow over to the variables and actually get a full menu of these. So you can actually load in the difference between these two. So if these functions, for some future functions, maybe trigonometric or exponential or whatever, if they're really quite involved, then rather than dealing with like where the two functions equal each other, which can get sort of busy and messy sometimes, I find that just actually disengaging them and doing a new y sub 3 function, which is the difference between them, now I'm just looking for the zeros of that function. And so what you actually see here is a new function that's been created. It's y sub 3. It's simply the difference between the two functions in question, and the two zeros of this function correlate to these two values, because if you're trying to find where one is above the other, well, that's where their difference is actually 0, and so you get the zeros coming out. So that you can confirm that this guy right here is 0.390, and if it's not, let me know. I'll buy you a brooch and for breakfast at school sometime. Okay, that's pretty much it. Crash course on some linear functions, quadratic functions, a little bit of inverse, looking at inequalities. Hope that was helpful.